Welcome to Model 9, Preventive Maintenance Effect on Reliability. In this model, we will demonstrate the effects of preventive maintenance on reliability in order to have clear this concept that the reliability can reestablish, the preventive maintenance can establish the reliability to a state as good as new, but not can improve, of course. We already had a chance to discussion about, we will have a chance to discussion about reliability growth in the second days of this training that demonstrate that reliability can increase when there's some design modification happen. But for a moment, consider that we have some equipment in the field that has some preventive maintenance or even replace. If you look upon the reliability and the effect of such preventive maintenance to establish the reliability, we will be able to predict the reliability, consider the maintenance uh, effect along the time. The other point is we are also able to observe the interval between failure of such equipment after the repair and the effects of the repair or even environment condition on such interval of failure. And then, of course, depends on the case, the interval of failure can reduce along the time. And we also demonstrate that in this model because of a very important concept concerning reliability in maintenance. Despite of having not as an objective of maintenance discussion in this model, it's important to consider that maintenance can take influence on reliability and equipment performance. And for railway industry, that's very important to consider that because in the end, higher than predict the reliability index as warranty as well as established during the run analysis, during the design phase and lifetime data analysis, we need also to predict the life cycle cost and the proper consideration of the effect of preventive maintenance reliability will enable to predict the expected number of failure of equipment. Before start, we present some glossary. Now we have some additional concepts such as repairable system and unrepairable system. Repairable system are systems which is necessary to carry out repair, preventive or corrective to reestablish the parts or total function. Unrepairable system are systems which is necessary to be replaced in case of failure to reestablish total parts or total function of such equipment. Reliability again is the success chance that some system or component has to complete its mission with uh, satisfactory quality during a specific period of time. Failure rates is the function that represents the failure occurrence on time. Operation availability is percentage of operational time which the system is available to fulfill their mission with expected service quality. MTTF is expected time which equipment may fail. MTTR is expected time with equipment may repair. And PDF is probability function which represents event occurrence. Of course, CDF is also the cumulative density functions such as reliability and unreliability. The new concept that we have here is repairable system and repairable system. We'll discuss in detail such concept further on in this model. So as we already defining here, reliability is a chance that some equipment or system operate during a specific of time without present of failures. And along the time, of course, the chance that has no failure reduced because the equipment getting aged. And that's condition get increase if we are putting the equipment in a hardest environment. So here in this axis Z, we have different temperature levels. So as higher as the temperature, lower will be the reliability related to the same period of time. So we can see here in 5,000 hours, if we have the reliability how close to is between 9% and 100%, consider 310 kelvins. But if you get the same temperature here, that is this line, 50,000 hours, and now you're starting to increase the temperature, we'll see that the reliability decreasing along the time depends on the level of the reliability until getting zero, depends on the level of stress that we have as defined here. So we have in 1300 in 330 kelvins, we expect to have almost low between 0 and 10% of failures as that we have here. So it's very important now to consider what we can do to avoid that such equipment failure. And in case of repairable equipment, we can carry out some preventive maintenance, establish its function. In case of replaceable, non-repairable equipment, there are the replaceable items. We can define the level of reliability that we need to replace such equipment. But what's the influence that we will have when we carry out such preventive maintenance? So that let's describe the concept of reliability considering the preventive maintenance. So reliability in a specific period of time is a reliability in time t where the preventive maintenance or replace happen multiply for the rest of time. So you have the time to the target time that you have from the preventive maintenance time that was carried out until the completeness of the mission that was defined for the reliability index. So if let's give an example. If no preventive maintenance is implemented in 3 years, we have a viable PDF considering this case, and then of course, if we have the parameters beta and eta in 3 years, we predict the reliability as 56% per 35. But now let's consider that we implement a preventive maintenance second year, and this concept is implemented in most of softwares and are described in books nowadays. So basically, we apply this equation above in here. Then by using the same PDF, beta and eta, but different range of time. So this time here is the time that's we consider preventive maintenance is in place, and this time here is the rest of the time to complete the mission. So we have the preventive maintenance 2 years. We're still using the 3.0 and 3.6 as beta and eta parameter. Multiply the 3 minus 2, so that 3 is the target time that we have for our reliability prediction is 3.04, and we're using 3 here. Minus 2 is the time where the preventive maintenance were implemented. So in the end, in the time 3, because we have implemented some preventive maintenance second year, the reliability will not go to level 56.35%, but will be in a level of 82.9%. So that is the concept behind of preventive maintenance effect on reliability that have a positive effect, are able to keep the reliability in a higher level. Despite is a concept proper as a concept that demonstrate that reliability is established. Behind this concept is not is considered that the reliability, even when we have preventive maintenance, will always decrease. So in this example, if we have more periods of preventive maintenance input in this equation, in some point the reliability will get lower and there is some failure. But in fact, that's not happen in a real case if we are able in all preventive maintenance to establish the equipment in a state as good as new, or even if we replace the equipment or components. Because of that, we consider that the proper equation, I consider the proper equation concerning the effect of preventive maintenance in a reliability is the same concept that we have here, but with one small issue. So this time here is not the time when the preventive maintenance happened, but the time after preventive maintenance. And then we have the time target minus the time after preventive maintenance. The point to put in the time after preventive maintenance in here is that it's after the time after preventive maintenance, the reliability will be 100% if we bring the equipment to a state as good as new. So the time then that means the zero here. That's the reliability time to be accounted from zero again, because in a state as good as new. And because of that, we have 100% this one in here. Multiply for the periods that is necessary to finish the mission that's in time t. So we will still have in the end the reliability in 3.04, not 82%, but 97.99% is higher. And then of course, whenever we go and in 2 years do again the preventive maintenance, we will keep such reliability in a higher level because we always multiply for one the reliability after the period of time. So graphically, what we are talking about here is represent for this graph that your reliability goes in some level down, and then at some point you in 2 years you're going to implement some reliability. So after the year two, when you implement some reliability after repair or replace, your reliability, if it's bring to state as good as new, is 100%. And then your reliability will decrease again for a specific period of time until 3 years. And this reliability, if you consider 3 years in here, will be this 7.99%. And that is this point in here related to time 3 years. And of course, after some times, this time you the reliability decrease again. You go implement some preventive maintenance. If you are able to bring your system to state as good as new, your reliability will be the 100%. And again, you multiply this 100% for the reliability for more 3 years, and you get again this 97.99%. And then you go further and further as long as you are able to establish the state as good as new, your reliability will always be reestablished for 100%. And during the specific period of time, it will always be the same because you will establish as good as new. I'm not saying that you always will be able to establish to the state as good as new. What I'm saying is if you are able to establish the reliability as good as new, your reliability will not decrease along the time. You will be able to keep such reliability at a high level and avoid the failures. In fact, we can see that in real cases when we are able to reestablish reliability in the state as good as new. But of course, in some cases, the reliability is not established and as good as new, and then as we have the stage between the degradation level or renewal between the two extreme point that's as bad as old and as good as new, from 0 to 100%, from 0 to 1. And then we'll see that for one, the case that the reliability is not established to as good as new. And then you see in the effect of interval of failure between failures, that's the reliability is not reestablished 100%. Considering the effect of preventive maintenance and maintenance repair and replace in equipment reliability, some concept that's also need to be clarified is the maintainability. We already spoken about that. The maintainability is a probability to carry out repair or replacing the system during a specific period of time. That's quantitative approach. We can also and concept. We also have the qualitative concept, that is the ability of an item to be retained in order to specify condition when maintenance is performed by personnel having specific skills, level, procedures, level of knowledge, procedure, and so on. And accessibility is also important when you're applying the concept of maintainability, is the possibility to access the equipment. So accessibility probability to access the system during a specific period of time to carry out specific repair. And also a design feature that's a qualitative concept design feature which affects the easy to of admission in area for performs a visual manipulated maintenance to carry out the maintenance, the repair or replace. The total downtime is the total time to establish the function. So that's very important for a run analysis. For example, what we are considering as a repair time is the total downtime that you usually need to consider the total downtime since the time that the equipment failing causes the downtime in the system until the time that this equipment is established its function by repair or replace in order to enable the system be available again. And the repair is the action that establishes total parts of system function, and replace is the change of such components for a new one. Also needs sometimes and reestablish this equipment function in a system. And inspection is action that check the component condition equipment, and it's important to regard the PF interval. PF interval is interval between the potential and function of failure. So some depends on the failure mode that we have. In case of degradation, we are able to detect the degradation as a potential failure, and carry out some actions to avoid the failure. So, for example, if we have a crack, we make some non-destructive tests, some measurements that's able to measure the equipment degradation, the thickness of the crack, and then predict when this crack will become a function failure that is considered a function failure. So in this case, a crack or a corrosion, we have a thickness measurement that's considered a functional failure. That means you should stop the equipment. So before that's happen, we can have some actions. That's very important concept. We're not to go through that. It's just important to understand the concept of maintainability and the concept behind maintainability, and also to understand the type of maintenance that we have. So usually we have preventive maintenance and corrective maintenance. The corrective maintenance happen after the equipment failed, and then we can or make a repair or replace. And preventive maintenance is the act to avoid the failures of the equipment. Then we have in preventive maintenance we have different types of preventive maintenance. We can have a schedule maintenance that is based on time, and this time is defined mostly based on or vendors procedure or standards, or even based on reliability. We have also the predictive maintenance, and predictive maintenance have different non-destructive tests that are able to detect the equipment degradation, as I mentioned before, in case of crack, and then based on it, we will predict when you do the intervention on the equipment to avoid failures, and we have the usual monitoring online. And then nowadays we also have prognostic maintenance management, health management that's enable not only to monitor the equipment, detect the degradation, but also trigger when some equipment needs to be repaired because it's close to the fail, or when the fail will happen. So that is all related to maintenance concept. Is important to understand when you're talking about maintenance that we can have different concept of maintenance. The one that we are defining here is the scheduled maintenance, and in the end, even for a predictive maintenance and online monitoring or prognostic health maintenance management system that detects failures and trigger the point that the equipment failed, in the end, all type of this different maintenance will go will have a specific period of time that will define a specific period of time when the equipment need to have some intervention. And in this case, such we need to measure the effect of such preventive actions, preventive maintenance in the system reliability. So just an example here, we have in a vessel, for example, we can have a reservoir vessel of brake system. And then for this equipment, we need to carry out a lot of tasks that's is part of the repair. So if you look upon what the whole total downtime that caused some activity is a huge time. So usually we have a repair time just to repair is a small period of time, but if you take into account different scenarios, pessimistic, optimistic of such each time for each task and consider repair, you see that the downtime is very higher that we have in here. And consider also to assess the equipment to start the repair is also a considerable time in a total downtime. And we need to consider the total repair time concerning the operation availability, and that's very useful for run analysis studies. So in the end, if I want to measure reliability, I need to make my prediction concerning reliability when this fail will happen a long time, but also consider how long it will take for repair replace. And that's the concept behind availability, because you're starting to account all downtime that shut down the system, and then you calculate the uptime, the system that the total time that system was available to operating in their capacity for the total nominal time. In this case, we have, for example, 20 units of hours, and we have 4 hours downtime, so we have 16 uptime, and then we divide the 16 for 20, we'll get to 8% of operation availability. So that is the concept behind operation availability. So is the percentage of total time of equipment system subsystem available to fulfill its mission. And usually we can express for uptime for total operation cycle time, nominal time, or we can add all the times that the system was available divided for total nominal time, and then we get the operation availability Concerning the equipments, are some concepts are important to define. So, what is a repairable system and unrepairable system? So, that's in the beginning. I described that repairable system are those which is necessary to carry out on repair. To carry out repair means preventive or corrective to reestablish part or total of the function. So, in a train, we have a compressor. In a locomotive, we have a diesel engine. We have a brake valves, bearing in different parts of equipment in the train, for example, bearing box in an axle. So all such components are repairable. And there are other components that are unrepairable, are those which is necessary to be replaced in case of failure to establish partial or total partial function. And usually such unrepairable are the electronics and electrical components, such as a fire protection sensor, a radio CPU, and TCMS components. So, based on such a concept of repairable and repairable, are also uh, input the concept of identical independence, identical distributed. So, independent means the maintenance, preventive or corrective, and other events that happen in the past will not take influence on equipment component performance in the future. So that's very applied for no repairable system. That's usually what we expect when we replace a new equipment come is input in the system, and then the past event, every effect of a repair, replace, or even considering the effect of operational condition, will not influence in the new one. So we have that when you consider sensors, transformer, electrical motors. So usually are electronic equipment that are non-repairable equipment. So this assumption has a limitation that such equipment can have degradation due to harder environment conditions. So, of course, if I now I install a new equipment, a new sensor, but now the environment temperature, for example, is higher for some reason or for a season issue, so we can maybe see that's the interval of failure in this new sensor will be lower and the reliability will be lower on time. And that's because the effects of environment. So that's the limitation of the concept of independence. Because independence do not only considering need to consider not only the preventive and corrective maintenance effect, but the environmental can also cause that. But usually, so independence are applied for non repairable items, and then that's clear that's the past items has no relation to the new ones because it's totally different. But identically distributed means that the equipment after repair or replace will have similar probability as function, or in other words, same failure behavior pattern on time. So same PDF do not mean exponential PDF. It's another concept that's when people talking about independent identically distributed, they related such concept only for electronics, and when you consider identically distributed, they consider exponential PDF. It's not true. So that means identical distribution. That's the equipment are in the same vendors and was produced in the same conditions, in the same process, in the same shifts. So they will have 100% chance to have the same failure pattern along the time. And then that can be applied for a repairable or no repairable equipment. So we need to pay attention on it. So I mentioned in the beginning that after repair, preventive maintenance, maybe some what we expect is that the as good as new condition reestablished, but that's only happen if there's no degradation equipment. So we need to be aware that when you have a specific components that you carry out some repair or replace and are able to reestablish the state as good as new, that will be fine. We establish that, but the equipment components in fact have different failure modes. So whenever we treat one of them, the other one is also latent in equipment or component. Then they can happen and trigger failures in equipment in some time in the future that will affect the reliability of the equipment as a whole. But if you consider the same failure mode, that will not happen, and that's we are considered that's what's bring to the state as good as new. So we need to be careful when you define that and when we define the effects of preventive maintenance. But mostly, of course, whenever we carry out a scheduled maintenance, we try to look on equipment in most of the equipment conditions to eliminate all potential failure modes to bring the whole equipment or equipment in a state as good as new. As as doing so, we will be able to bring the equipment as good as new. And if you look on the interval of failure of such equipment along the time, this interval of failure will keep constant. And the Kijima factor demonstrating that. So the age is established based on the last intervention. This is Kijima factor 1. And the age is established based on the all intervention is Kijima factor 2. So what does it mean? If we are able to establish the condition of the equipment after replace or repair to as good as new, the interval between failure will always be the same. But if it's not, the interval will reduce. It is not will reduce between 0 and 100%, will be lower than 100%, and then the further interval of failure will be reduced compared to the first one. So let's take a look on how is this concept is expressed in terms of mathematics. So we have here the demonstration of the equation to calculate the degradation factors and based on the Kijima model. So HE is the time between failures, the time between if less one and if a failure. So and the key is the restoration factor. So if we have 100% of restoration factor, we have the state as good as new, so key equal to 1. If we have 0% of restoration factor, we have the state as bad as old. So and here the xi is the age in time x and the age in the previous period. So based on it, we can carry out an exercise where we had interval of failure, that's this age here is 2 years. So and we have the 50% of restoration factor. So after the repair and the replace, there was a degradation of 50%. So we look upon what was the time that was the last intervention. So was the time 4, and then we will predict when will be the next fail. So the failure will happen in time 5. So now we can see that the interval of failure that was 2 before now is 1, and then the next failure and intervention need to be done in time 5. So there is a difference between time 5 and time 4 because there was 50% of degradation. So the other Kijima factor 2 is also is represented for a different equation, but have in the end the same factors that we have in here. So we have the time between failures, restoration factors, and the age of the equipment along the time. So let's look on graphically what's happened if we are able to bring the stage to as good as new. So we have an equipment operating 2 years. So after 2 years, there is some preventive maintenance. Bring the system to a state as good as new. So it will take more 2 years to have some intervention on some failures. That is time 4. So in this case, we have the time as good as new. So if you look on this equation here, if you put 100% of degradation here, we have 4 plus 2, that's 1 plus multiply for 2, we have 6. Then again, if this time here is 6 in the age 3, that means that the time interval between failure is 4 plus 2. That is still the time between failure is still 2. So that will be 100% of degradation of for restoration factors, and then that's means that systems bring to the state as good as new. But let's look at an example that we gave. So we have the first event in here in 2 years. We carry out some preventive maintenance. There's no human error during preventive maintenance. The equipment is in a state as good as new. And again, after 2 years, we'll have the failure again. So the interval in here between 4 and 6 is 2. So in this time, that's the next failure happens after 4, is 4, multiply for restoration factor is 100%, multiply for this interval of failures is 1. So we have 2 plus 2 multiplied from 1 is 4. And then what we're expecting here, that's the case that we demonstrated 50% of restoration factor, that was 50% of degradation was, we have now in time 4 multiplied for restoration factor, that's 50%, multiply for the previous interval to failure, that's 1. So we have now 1 is the interval of failure. So the age here will be in 5, and that's what's demonstrated in this graph. So the other model, that's the renewal model, is the model that we use also to calculate the age of the equipment along time, consider the restoration factor, and consider if the stage is not in as good as new. Of course, to measure the restoration factor, we need to look upon the interval of failures, and then we will be able to measure the restoration factor. And we can use that when you're modeling, for example, the run analysis. It's very important to apply such concept in run analysis. Okay, so here, just to look upon some example of identical, we have these 3 components. The 3 components are in series in RBG. That means if you want to fail, that's the impact on the system. So we can see what's happened along the time with these 3 components. Now, there we apply here exponential PDF, different exponential PDF, and then we'll see the effects on the system. So that's is the condition of the failure of such equipment. There is no degradation here, but they are random failure, exponential failure. So now let's consider normal PDF. That's the easiest case to look upon the effects of restoration factors. So we have in a state as good as new. So if you look on the components C, B, and A, we can see that interval of failures remain the same along the time. And then, of course, that is the restoration factor 100%. We have a state as good as new for each component. And then, of course, considering the impact of the 3 component system, we have this profile of failure. But let's consider now that we have degradation of 50%. So now we can see that the failure or more, the interval of failure after the first uh, repair or replace or preventive maintenance reduce along the time. So now there is a degradation. There's not possible to reestablish after this preventive maintenance the restoration factor for 100%. And then that will affect, of course, the system. So that's what we need to consider as the effects of preventive maintenance, not only in case that we have a stage as good as new, carry out some preventive maintenance to establish the reliability, but have in mind that in some case there will be degradation or for the equipment age or even for a human error triggered during your maintenance, that's make that the interval of failure will reduce along time. And then, of course, that will also affect the prediction of reliability. But that is the focus of the training, considering the run analysis training. That's also is available if you want to go through this concept and model the system, not to look up on only one individual equipment and components. Okay. So thanks for your attention. If you have any questions, please send me an mail and I will answer you.